Hi everybody. We're about to start a new section. Next few weeks we'll be talking about circles. There are lots of interesting things to be learned about circles. It'll be fun to do it for the next few weeks. We're going to show and label each part. We're going to learn about these parts and attributes of circles. Consider the circle at right is circle A. And how does one name a circle? A circle is named by its center. So if this is circle A, then its center must be point A. I was thinking about that and was wondering about a circumstance like this when we have a pair of circles with the same center. Those are concentric circles. I guess we just have to say the smaller of the two concentric circles, but you can have a larger one, or if you had a few of them, it might be more interesting still, but generally speaking, a circle is named by its center. And then we have concentric circles. Those are both circle A. We have a large one and a small one. We can talk about it that way, but back to this circle in general. Show and label these ideas, and radius AB. What's a radius? Well, radius is a measurement, but it's also a chord. It's a segment, not a chord, but a segment. From the center of the circle to a point on the circle. Didn't have to go to that point, but it could. There's segment AB, and that's chord. That's radius AB. I do have to talk about a chord BC. A chord is any segment who has both endpoints on a circle. This B is already in place. I could show a point C right here. And both of those points being on the circle, B and C, makes that chord BC, a segment with both endpoints on the circle. And then it asks me to show diameter CD. A diameter is also a chord, but it's a special chord. It's the longest possible chord of a circle. It's a chord that passes through the center. I'm supposed to show diameter CD, and there she blows. The longest possible chord, a chord passing through the center is a diameter. And then I'm supposed to show a tangent line DT. What is a tangent to a circle? A tangent is a line that it is coplanar with a circle and touches a circle at a single point. Since D is on our circle, and we're going to show tangent line DT, this line must touch circle A at just that single point. Showing that as carefully as I could, we're going to study tangents a lot. That line appears tangent to circle A. Let's show the full line. Tangent line DT. This is point D, and I got to put T somewhere, anywhere I want along that line, and there's tangent line DT. A little heads up ahead of time, though. You might be wondering, what do you think about this angle or that angle? Look like they might be congruent. I think so too. And since they add up to 180, I think they're going to be right angles, aren't they? Something we're going to be using in the next days is if a line is tangent to a circle, then it's perpendicular to its radius at the outer endpoint. You can expect those to be right angles when you have a tangent line. We're also supposed to show a secant line BD. A secant is a line that intersects a circle at 2 points. Different from a tangent in that respect. A tangent touches a circle at a single point, and a secant line touches a circle at 2 points. Since it called it BD, then I had to use those 2 points. And here's my secant line, BD. There's my sketch all decorated with these attributes. I have a radius AB, a chord BC, the longest possible chord, the diameter CD, a tangent line DT, and a secant line BD. Let's show some more ideas. Circle P. I know a circle's named by its center. That must be the center there. Chord AB has length 16. The radius of the circle P is 12. I can show lots of different radii, but let me show radius PA. I know that length should be 12. I could have shown any other radius from P to B, and it would have also been 12. How far is AB from the center? And I got to ask you, if here's a point, and over here's a line, how would you measure the distance from that point to that line? It would have to be perpendicularly, wouldn't it? As we measure the distance from a point to a line, it would be done so perpendicularly. That's how far that point is from that line. It would be this distance. So, when we're thinking here, how far is AB from the center? We would want to show the line that's perpendicular to it. And the question I have for you now is, if that's perpendicular, Did it cut this chord into 2 equal parts? Is that something we can be sure of? Because I understand that chord AB is of length 16. Are those 2 parts going to have to be 8? And I want to talk about that with you for a minute. So I'm going to turn this page over, and I'm kind of ready to do that. You might want to make a sketch like this and slow the tape down, but let me tell you what's up. Here's the thing I want to prove. If XY is perpendicular to AB, if this is a right angle here and there, if those are right angles, then XY bisects AB. That's what we're going to establish. We're going to go ahead and do this proof just like we used to. What would be given? Statement 1. Given is XY is perpendicular to AB. If that were given, what would we want to prove? In fact, we would want to prove that XY bisects AB. That would mean that these 2 parts are congruent. Just say it that way, though. XY bisects, cuts in 2 equal parts, AB. And we're going to make that proof happen right now. And the way we're going to make it happen is going to get a couple of congruent triangles here. The way we're going to make those couple of congruent triangles, we're going to show a couple of radii. My statement 2 will be, show radii XA and XB. Show radii, double I, plural of the word radii, XA and XB. Do that right away. Show this radius and that radius. What makes you think you can go around showing radii like that? And I said, well, the circle's got lots of radii. The circle truly has infinitely many radii, but I can show these 2. I'll say the circle has many radii. As many as we need radii. Would those radii be congruent? Bear in mind, I'm wanting to get these triangles to be congruent, and I think that this radius is going to be as big as that radius. I'm sure of it. Going to make that statement. We'll talk about it right away. XA is necessarily congruent with XB. Just because they're both radii of the same circle, you're pretty sure they got to be congruent? I say, yes, sir. The definition of a circle is a set of all points a fixed distance r, the fixed distance that is the radius, from a fixed point that is the center. Yeah, those are all going to be the same distance, aren't they? I'm going to say radii are congruent. That's my rationale for statement number 3. So now, how are we going to get these triangles to be congruent? I know that I have right angles already. I want to prove that this is the midpoint of AB. What about XY congruent to itself? I'm going to put a few marks on that. I know it's true that XY is congruent to XY by the reflexive property. Will that help me get those triangles to be congruent, I wonder? And it's fairly obscure how we're going to get these triangles to be congruent. Not terribly obscure, but the hypotenuse of this one matches the hypotenuse of that one, and this leg matches itself, and that's hypotenuse leg. Triangle AXY is congruent with triangle BXY by hypotenuse leg. We didn't practice that one much last semester because, well, I wanted to get to right triangles before we talked about it, but doesn't it make sense if the hypotenuse match and one of the legs matches by the Pythagorean Theorem, those other 2 segments would be the same. So we have congruent triangles by hypotenuse leg. And what do you want to do with your congruent triangles anyway, mister? I'll take a look. We wanted to prove that XY bisects AB. What would make you think that XY bisects AB? If AY is congruent to BY? Yeah, those are corresponding parts of those congruent triangles. They would have to be congruent. And on our 7th step, if AY is congruent to BY, I guess Y's got to be the midpoint, doesn't it? This segment's been bisected. I'll say it that way. XY did bisect. It bisects AB. Just because it don't broken into two congruent parts. You think it bisected it? And yes, I do. That's by the definition of bisector. Whether it be an angle bisector or a segment bisector, it's been divided into two equal parts. But stay with me a little while longer. What would be the converse of that theorem we just did prove? I think we're going to need it also. This time, same idea, same sketch. We're going to start with xy is the bisector. xy bisects AB. And we're going to prove what we just used as the given, that in fact it would be perpendicular to AB. That xy is perpendicular to AB. When we have this theorem and its converse proven, then we'll be able to go back to work on that little workout that's on the other side of this page. Let's jump in and make this happen. So we know that xy bisects AB. That makes me think that these segments would be congruent, huh? I'll call this statement 1, and here comes statement 2. If xy does bisect AB, then AY is congruent with YB. Because that's what happens when you bisect something. We got cut in two congruent parts. Statement 2 must say definition bisect. I am going to try to get congruent triangles here. We might as well go ahead and show those radii. I'll make a statement first. Show radii XA and XB. Happy to do just that. What makes you so sure you can go around showing those radii? And a circle has infinitely many radii. This circle has many radii. Statement 4. Looking for a way to get these triangles to be congruent, and then we're going to prove that we have right angles. Yeah, these radii are going to be congruent, aren't they? Let's make that statement that XA is in fact congruent with XB. Radii of the same circle are necessarily congruent. I just going to scribble radii are congruent. And then my fifth statement. Sure, we'd like to get these two triangles to be congruent. Then we can talk about why these are right angles. Isn't XY congruent to itself? Our friend, the reflexive property, can make this workable? XY congruent to XY by the reflexive property. So have you got congruent triangles or what? Yeah, I think I do. Triangle AXY is congruent with triangle BXY. How did you get your triangles to be congruent anyway? Side, 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 huh? Got all three sides of this one matching all three sides of that one. But, homies, what we are to establish is that XY is perpendicular to AB. Let's call this angle 1 so we can talk about it, and this other one below it angle 2. And we are to establish that these lines are perpendicular. Angle 1 and angle 2 are going to have to be right angles. Are angle 1 and angle 2 congruent? Are they corresponding parts of these congruent triangles? I figure they are, huh? Let's make that statement. Angle 1 is congruent with angle 2. Corresponding parts of congruent triangles are necessarily congruent. What else do you know for sure about angle 1 and angle 2? They do make a straight line together, don't they? Yeah, they're a linear pair. They must be supplementary. I'm going to say angle 1, make that better. Angle 1 and angle 2 are supplementary. Because any linear pair has to be supplementary. If it's a linear pair, then it's supplementary. These angles are a linear pair, therefore they're supplementary. And now I think these angles are congruent and they're supplementary. So what must be true then? If angles are congruent and supplementary, then they are right angles. Angle 1 and angle 2 are right angles. Two angles, congruent and supplementary, implies they are in fact right angles. These angles were congruent, equal in measure, and they're adding up to 180. Yeah, they're going to be 90 apiece, aren't they? And I think that finishes this proof pretty much. I could conclude that XY is perpendicular to AB. It does form right angles, therefore by golly it's perpendicular, huh? XY is perpendicular to AB. What makes you so sure? Well, that's what it means to be perpendicular, by the definition of perpendicularity. Now, that was fairly painful perhaps to get these proofs done, but now we have all the tools we need to get back and get this page figured out. Let's go back to work. We knew that the radius of the circle was 12 and chord AB has length 16. We wondered how far AB was from the center, and we measured that distance perpendicularly. You say, well, if you go to that chord perpendicular, you have bisected that chord. That's what we just did prove. And since AB had length 16, this length would have been 8, and that length would have been 8. And we're going to find this little length that I'm going to label as X. That's how far AB is from the center. Hit it with the Pythagorean Theorem. X squared plus 8 squared must equal to 12 squared. So we know that x squared plus 64 is equal to 144. Subtract 64 from both sides, and we know that x squared is equal to 80. Taking the square root of both sides of that, x is equal to, what do you know about the square root of 80 anyway? Yeah, it is 16 times 5, isn't it? Therefore, it must be 4 times the square root of 5. That's what this length would have been. That's how far AB is from the center. It's 4 root 5. Let's turn to tables a little bit. Same idea. Chord PQ has length 8 and is 6 from the center. That distance measured from the center would have been measured perpendicularly. I just did bisect that chord, huh? The chord has length 8, so this length must have been 4, and that one would have been 4. And 6 is 6 from the center. This length has to be 6. That's how far it is from the center to chord PQ. Find the length. So the process is you find the radius and the length of the longest possible chord. We could show radius CP or CQ. I'm going to show CQ. And I still have a right triangle to work with, don't I? We measured that distance perpendicular. We got a right triangle. Let's hit it with 6 squared plus 4 squared equals that hypotenuse, which is in fact the radius, isn't it? Let's call it R. Is equal to R squared. And we got 36 plus 16 is equal to R squared. Those add up to 52 is equal to R squared, and we'll take the square root of both sides. What do you know about that 52, isn't it? 4 times 13. So our radius must be 2 times the square root of 13. But what do you think about the length of the longest possible chord? Remember up here that the longest possible chord is a diameter and it has 2 radii in it, doesn't it? So I'm just going to tell you that the diameter has length twice this amount, 4 square roots of 13. There's our longest possible chord. Let's play some more. In circle X, circle is named by its center, chord PQ is 4 from the center. Let's show that idea. And if we're measuring the distance from that point to that line, you would measure that perpendicularly. Since you've gone to that chord perpendicular, you have bisected said chord. PQ has length 8 root 3. I'm going to go ahead and call that M right there because it is a midpoint, and that length right there would have been 4 times the square root of 3, as that length PQ has been bisected. It's 4 from the center. This length had to have been 4. Find the length of the radius and the length of the longest possible chord. Let's show a radius. Let's hit it with the Pythagorean Theorem. You might know something about these couple of numbers, how that hypotenuse is going to look for the radius. I'll call the radius R. And it would be 4 squared plus 4 root 3 squared is equal to the hypotenuse r squared. You might know something about these numbers already. We've got 16. And when you square that 4 root 3, you got to square that 4, going to get 16. You're going to square the square root of 3, get a plain old 3. That's 16 times 3, isn't it? That's 48 is equal to r squared. That's 16 times 3, and got another 16 right there. That's going to be 16 times 4, isn't it? That's 64 is equal to r squared, and we'll take the square root of both sides. So now we say the radius had to have been 8. Yeah, that must have been 8. And you're thinking, well, that's a special triangle right there, isn't it? That's a 30, 60, 90, isn't it? Short side was half of the hypotenuse, and the longer leg is the short side times the square root of 3. That's interesting because we could have figured some angle measures and maybe some arc measures, but that's going to be a little later. Give the length of the longest possible chord. I know the radius is 8. So what about that diameter? The longest possible chord. Yeah, it would have been 16, huh? One more time with feeling. Same idea, but we're going to give you different lengths this time. The longest possible chord is 26. Chord AB is 5 units from the center. Find the length of that chord AB. 5 units from the center, you say. So I'll measure that distance this way. The distance from the center is measured perpendicularly. Since I went to the chord perpendicular, I have bisected that chord. The longest possible chord is 26. So what about I guess the longest possible chord was the diameter. And if the diameter is 26, then the radius had to be 13? Yeah, that makes sense. That'd have to be true, doesn't it? And chord AB is 5 units from the center. We measure the distance from this chord to the center. That unit length is 5. Let's call this length X right there, and you might know that length already from that midpoint to segment to point B. 5 squared plus X squared is equal to 13 squared. Yeah, these seem like familiar numbers to me. 25 plus X squared is equal to 169. Subtract 25 from both sides. We got X squared equals 100.